Let's talk about reality, not in a philosophical way, but in a very basic physical way. Why is a chair a chair? Why is it solid? Why is it right there in one place and not smeared out across the room? You can touch it. I can touch it. We both agree it exists and where it exists. This seems like a silly question. Of course, a chair is a chair, but underneath it all, the world isn't like that. The world is quantum, and the quantum world is deeply strange. It's a world of possibilities, not certainties. A tiny particle, like an electron, isn't really in one place until you look for it. Before you look, it exists in a state of what's called superposition. It's in a haze of all possible places it could be, all at once. It's a wave of potential. Only when you measure it, when you interact with it, does it choose a location. The wave of possibilities collapses into a single solid point. This is one of the fundamental rules of the quantum game. This leads to the biggest puzzle in all of physics. If everything is made of these quantum particles, which live in a ghostly world of superposition, why isn't everything else like that? Why isn't the chair you're sitting on in a superposition of being in your room and also in your kitchen? Why isn't the moon in a superposition of being in the sky and also crashing into the earth? The big world we see, the classical world, is solid and predictable. The small world that builds it, the quantum world, is fuzzy and probabilistic. How do you get one from the other? How does the definite classical reality we experience emerge from the indefinite quantum reality underneath? For a long time, the answer was basically, well, an observer looks at it. This was part of the old school view, the Copenhagen interpretation. A conscious observer, or at least a big measuring device, forces the quantum system to make a choice. But that's not a very satisfying answer. What counts as an observer? A person? A cat? A camera? A rock? Where's the line? It feels like you're hiding the magic in a black box called measurement. It doesn't explain the process, it just states the outcome. This is where a newer idea comes in. An idea called Quantum Darwinism. It offers a different and maybe more complete explanation. It says there's no magic in measurement. There's no special role for a conscious observer. The secret ingredient that turns the weird quantum world into our solid classical world is the environment itself. The name Darwinism gives you a big clue. It's about survival of the fittest. But here, we're not talking about animals or genes. We're talking about physical states. Quantum Darwinism proposes that certain quantum states are better at surviving and reproducing in the environment than others. The states that are fittest are the ones that become our shared objective classical reality. The world we see is the world that was best at getting itself copied. To understand how this works, we need to add a character to our story that we usually ignore the environment. In old quantum physics problems, you often think about a particle in a vacuum, a perfectly isolated system. But nothing is ever truly isolated. That chair in your room isn't in a void. It's sitting in a room full of air. It's being bombarded by trillions of photons from the lights in the sun. It's interacting with the floor. It's bathed in a chaotic, messy, information-rich environment. This constant interaction is not just noise. It's the key. This process of the environment constantly poking a quantum system is called decoherence. Let's think about that electron again. Imagine it's in superposition of being in two places at once. Let's call them spot A and spot B. It's a delicate, fragile state. Now, a single photon from a light bulb flies across the room and bumps into it. What happens? If the electron was at spot A, the photon would bounce off in a particular way. If the electron was at spot B, the photon would bounce off in a different way. So, by bouncing off the electron, the photon has now picked up some information. The state of the photon is now tied to or entangled with the state of the electron. If you could catch that photon, you could, in principle, figure out where the electron was. But it's not just one photon. It's a constant flood of them. And air molecules, too. Billions upon billions of tiny environmental particles are bumping into our electron every fraction of a second. Each one of them gets entangled with the electron. Each one carries away a little piece of information about its location. The superposition was a private affair. It was the electron's own secret. But now, that secret has been leaked. The information about the electron state, is it at A or B, has been spread out and scattered into the vastness of the environment. The original clean superposition is destroyed. It has decohered. The electron is now effectively forced into a definite state, either A or B, because the environment has measured it. The decoherence is the first step. It explains why we don't see large objects in superposition. A cat, a chair, a dust mote, they are so big and interact so strongly with their environment that any quantum superposition they might have had would decohere almost instantly. The environment is constantly monitoring them, pinning them down to a single state. This is why our world seems classical. Decoherence kills the quantum fuzziness for anything big enough to notice. But this raises a new question. Decoherence explains why a choice is made, but it doesn't explain why we all agree on the choice. If the information about the electron's position is scattered into the environment, it's lost, right? It's like whispering a secret into a hurricane. How can I, an observer, learn anything from that mess? And if I do learn something, how do I know you'll learn the same thing? How does objectivity arise? If I look and see the electron is at spot A, why do you also see it at spot A? This is the brilliant part of quantum Darwinism. It says the information isn't just lost, it's copied. And it's copied in a very specific way. Let's go back to our electron in a superposition of spot A and spot B. There are many properties the electron has. It has a position, it has a momentum, it has a spin, but not all of these properties are created equal when it comes to interacting with the environment. Some properties are tough and stable, some are fragile. Think of it this way: an object's position is a very robust property. If a photon bounces off a bowling ball, it gets a very clear picture of where the ball is, and it barely affects the ball's position at all. The position information is easily imprinted on the photon. The same is true for the next photon, and the next, and the next. The position of the bowling ball is a stable property that survives interaction with the environment. These stable, robust states are called pointer states. They are the states that the environment can easily find out about without messing them up too much. Other properties might be more delicate. Maybe the bowling ball also has some weird fragile quantum vibration. A photon bumping into it might completely destroy that vibration. The environment can't get a stable reading of that property. It's not a good pointer state. Quantum Darwinism says that the environment is like a massive broadcasting system. It interacts with a quantum object and picks up information about its pointer states. And it doesn't just make one copy of this information, it makes billions and billions of redundant copies. So, for our electron, its position spot A or spot B is a very good pointer state. When the flood of photons interacts with it, some photons will interact with the spot A version of the electron, and others will interact with the spot B version. But the interaction doesn't just destroy the superposition, it creates a record. A photon that bounces off the spot A version now carries the information it was at A. A photon that bounces off the spot B version carries the information it was at B. The environment, that cloud of photons and air molecules, is now filled with information. But here's the Darwinian part. Let's say the system collapses to spot A. What happens is that the part of the environment that interacted with spot A survives, and the part that interacted with spot B effectively dies off. Suddenly, the entire cloud of interacting particles is filled with countless little messengers all carrying the same memo. The electron is at spot A. The state at spot A has successfully imprinted itself over and over and over again onto the environment. It has reproduced. The state in a superposition of A and B was not good at this. It was fragile, it died out, the state at spot I was fit. It survived, it was naturally selected by the interaction with the environment. Now, think about what an observer does. You and I don't interact with the electron directly. That's impossible. We are part of the environment too. To see the electron, our eyes just need to catch a few of those photons that have bounced off it. We are sampling a tiny fraction of the environment. What information will we find? We won't find the confusing, mixed up information of the original superposition. That has been washed away by decoherence. Instead, we find the information that was successfully copied and broadcast everywhere. Because the environment is flooded with redundant copies of the message. The electron is at spot A, any small sample we take is almost guaranteed to give us that message. The few photons that enter my eye will say A. The few photons that enter your eye will say A. A photograph taken by a camera will record A. This is how objectivity is born. We all agree on the properties of the world because we are all independently reading from the same massive public bulletin board, the environment. The environment has filtered out all the fragile quantum possibilities and selectively amplified the stable classical states. The reality we agree on is the one that was fittest at leaving copies of itself scattered all around us. So, the chair is solid and in one place for two reasons. First, decoherence. It's so big and interacts with its environment so much that any quantum superposition is destroyed in an unimaginably small fraction of a second. It's pinned down. Second, quantum Darwinism. Its position is a very stable pointer state. It constantly imprints information about its location onto the photons and air molecules bouncing off it. This creates a massive, redundant cloud of information about its position all around it. When we look at the chair, our eyes are just sampling that information cloud, and because the information is so redundant, we all get the same answer. The chair is there. This idea fundamentally changes our view of information. In the classical world, information is something we create. We write it in books or store it on computers. In the quantum world, according to this theory, information about a system is constantly and automatically being copied into the environment. The world is constantly writing its own biography, and we just happen to read snippets of it. It also demystifies the observer. The observer is no longer a magical entity that collapses wave functions. An observer is just any system that can acquire and process information. A human, a dog, a camera, or even a simple rock are all, in a sense, observers. They are all parts of the environment that can become entangled with a system and store a record of its state. You are special only in that you have a brain that can consciously interpret that information. But the physical process of recording the information happens with or without you. Think about what this means. The entire universe is a web of interactions. Every particle is constantly measuring every other particle it comes into contact with. This cosmic scale process of decoherence and selection is what carves out reality from the raw marble of quantum possibility. The classical world isn't a fundamental layer of reality, it's an emergent property. It's the consensus reality that wins the Darwinian struggle for existence. It's the pattern that survives the constant chaotic scrutiny of the environment. Of course, this is still a theory, and it's not without its own set of questions. For one, it doesn't fully solve the measurement problem for everyone. It explains how a system comes to appear classical to the outside world. It explains why we all agree on its properties. But what about the system plus the environment as a whole? From a God's eye view, isn't that whole combination still in one giant quantum superposition? Quantum Darwinism explains the emergence of the classical world for us as subsystems within the universe. But it might just be pushing the ultimate collapse question one level up. Also, the transition from quantum to classical isn't a sharp line. It's a spectrum. A tiny, isolated system is purely quantum. A cat is overwhelmingly classical. But there's a middle ground, the mesoscopic world, where things are big enough to be complex but small enough to still show quantum behavior. This is the world where scientists are building quantum computers. In that world, the environment is your enemy. You have to fight decoherence with everything you've got, shielding your quantum bits from any stray interaction that could leak information and destroy their delicate superposition. Quantum Darwinism provides the theoretical framework for understanding why that fight is so hard. You're fighting against the universe's natural tendency to select for classical states. Let's try one more analogy. Imagine a secret message written in invisible ink that is also water-soluble. This is like a quantum superposition. It's there, but it's hidden and fragile. The environment is like a damp, misty fog that is constantly swirling around the paper. As the moisture touches the ink, two things happen. First, the ink starts to run and blur. The original, delicate message is destroyed. This is decoherence. But now, imagine that the ink also has a chemical in it that reacts with the paper when wet, leaving a permanent dark stain. The pattern of the original message is now burned into the paper itself, and not just one copy. As the moisture spreads, it creates multiple slightly blurry but still readable copies of the message's pattern. The original fragile information is gone, but has been replaced by many robust, redundant copies. This is the selection part of quantum Darwinism. Now, anyone who comes along later can't see the original invisible ink message. It has decohered, but they can easily see the dark stains on the paper. And if you look at one corner of the paper and I look at another, we will both piece together the same message. We have an objective shared reality about what the message was, not because we saw the original, but because we are both looking at the surviving, fittest copies. This is the essence of the idea. The world we perceive is not the deep, underlying quantum truth. The world we perceive is the collection of stains left on the environment. It's the public record. The most stable, repeatable, and robust aspects of the quantum world are the ones that manage to stamp themselves all over their surroundings, and it is these stamps that we collectively call reality. So quantum Darwinism doesn't get rid of the weirdness of quantum mechanics. Superposition is still real. Entanglement is still real. but it suggests a natural physical process for how that weirdness gets hidden from our everyday view. It's a story about information, about how some information is private and fragile while other information gets copied and broadcast to the world. And it's the broadcasted information, the information that survives the scrutiny of the environment, that forms the world we know. The chair is a chair because the state chair is incredibly good at telling the rest of the universe that it's a chair. It has won the cosmic game of survival.